want to talk about a file system I built and a bit about file systems in general. So I'm going to start with a brief introduction, first about myself, then about Neo4j, which is I work for Neo Technology, a company that builds Neo4j. It's a graph database. Then I'm going to talk about what are file systems and what are some, if not problems, but issues, maybe complications that you run into with today's file systems. And I'm going to talk about what we, as in the database, needs from a file system. And then I'm going to talk about a file system I built myself. That's the DBFS part and the internals of that and how that works. So my name is Chris. You can follow me on Twitter if you want. It's mostly geeky stuff. And I write database systems for fun and profit, and somehow found myself writing a file system for fun and profit as well. So I specifically work on Neo4j. It's the world's leading graph database. It's awesome. It's an async transactional database. It stores a graph that has vertices and edges or nodes and relationships, labels, properties. Then there's a query language that you can use to query the graph and traverse it and stuff. It's called Cypher. It's awesome. I'm not going to say any more about that. And it's a single image database, which means that on every machine, every installation where you have all the data fit on the machine. And then for high availability, we replicate the transaction log and copy over the data. So every machine in a cluster would have the exact same data. So it's fairly normal in that sense. It's not distributed in like Cassandra. So from my perspective, as I work on the kernel, the internals of the database engine, this is a very simplified picture of how I see it. So we have transactions that begin, and you do some queries. Maybe you accumulate some transaction state by doing some writes and modifications. Eventually, you hopefully commit. And then we serialize the transaction state into commands and write it to the transaction log. And when we fsync the transaction log, the stuff that we wrote to the log is made durable on the storage device. And then we take the commands and then we apply it to the store that we have in memory. So we have our own page cache that caches the files in memory. And we apply through the cache. So we don't actually have to do very much I/O when we commit a transaction. We don't have to do the log write. That's the minimum we have to do. And then at a later point, we have a background process called checkpointing that notes the current position of the last applied transaction in the log, remembers this, and then it flushes all the dirty state we have in memory, writes it to the files, fsyncs each one, and then it adds a checkpoint entry to the log that will point back to the log entry we remembered before. So when we do recovery, find the entry, then we can go back to that point and reapply all the transactions, and then it's in a consistent state again. So two things are important here. One is that we have our own page cache, which means that we have a single entry point to access the store files. So that's one abstraction that kind of guards this. And another thing is that we have files, of more than one file. So we assume that we can put all our nodes in one file, all the relationships in another. And of course, the transaction log is also a file, but it's in a completely separate component, so I'm not going to talk about it. And it's not going to be relevant here very much anyway. So file systems. And the idea is conceptually quite simple. You basically have the illusion of organized, durable, and dynamically growing named giant arrays of bytes. And you can just add to them and change stuff, and they will be saved. And when you restart the process of the machine, they'll still be there. And this abstraction is provided on top of a giant arrays of bytes. These are the blocks on the storage device. The 4K or 16K on SSDs, 512 bytes on spinning disks. So initially, it was quite simple. The earliest file system didn't even have directories, but as people started using more, building more advanced systems, they realized that directories and some kind of hierarchy was kind of useful. So they added this, and it became part of normal APIs, and they added buffered I/O initially in userland, but then they also added the virtual memory to CPUs and operating systems, and this became a central part of operating system that they cache file contents in memory for you, and it's transparent. And many file systems have a journal, very similar to the transaction log that we have in a database, and it guarantees and protects the consistency of the metadata within the file system, and occasionally even the contents of your files as well. So as time goes on, people want more of the file system. They add permissions, modified times, and they grow to have quite a lot of features. And from our perspective, we don't really need all that much. Some of these are quite esoteric. Some of them are quite bad. For instance, resource forks. If you haven't heard about them, don't look them up. But also, supporting all of this means that you need more code in the file systems, and a good indicator of how many bugs you have in a piece of software is just how many lines are there. So more lines of code, more bugs. They've actually done studies of this. It's not a bad metric, surprisingly. So file system internals is one thing. The APIs they expose is another. And it's actually surprisingly subtle to safely write to a file and have it be consistent, not corrupt, durable. So if we have a file that says a space foo, we want to make it say a bar, you'd think that the pwrite function would be perfect. So we write these 3 bytes at offset 2. So that would change a foo to a bar. But it turns out that with the blocks, the boundaries, all this caching that goes on, these individual bytes can actually be split up into multiple IOs, and they can be written in any order. So if we have a crash at some point, we can end up with a far or a boo or any other combination. So we need to protect our files. So one thing we can do is we can add an undo log. And what we're doing here is that we create a log, and then we record the data that we are about to change. And then we do the change, and then we delete the log file. So if we crash and then we start up again, we see the log file, we can say, I don't know what I was supposed to do, but I can undo it by just doing this call, but with foo instead, because I recorded that was the previous data. So on X3, this actually works with data journaled. So there was a paper on this at a OSDI conference back in 2004 that went into what guarantees to file system actually provide, and then they went through this example that I'm showing you. So they examined a lot of file systems. I'm just going through X3. So it works on data journal, but it doesn't work on data ordered, which is the default, and it doesn't work on data write back, which we'll get to. So what can happen is that for data ordered, the write to the log and the write to the file can move around. There's no ordering between them, which is inconvenient if we want to rely on the log. So we can add an fsync to the log, and what this does is 2 things. It makes sure that the data is durable in the log, and it also inserts a barrier that orders writes before it and writes after it. So now these 2 writes can no longer switch around. But with the write back, we're actually only guaranteeing the consistency of the metadata. So what can happen is that we extend the size of the log, but if there's a crash in this write or the fsync, we can end up with a log that has grown, but the data has not been written. So there's going to be have some garbage. So we can fix this by adding a checkpoint to the log entry, and now it works on all of these configurations of ext3. So that's not all file systems. It turns out that the APIs don't really say very much about the ordering of file operations and directory operations. So what could happen is that if we get a crash, we had created the log file, but we did not fsync the directory. So even though we've written to the log, it doesn't exist. So we have to fsync the directory after we've fsynced the log file. So now we know the log exists. Then we have to fsync the file. So when we delete the log, and then we fsync the directory again, then this will work on almost all file systems in almost all configurations. But that's not all. It turns out that if fsync actually doesn't persist the data, doesn't make it durable, which some file systems like OS X is like that, then we have to do another different file system call to force it to flush the buffers all the way through. And even then, the hard drive can actually choose to ignore it. And the reason they do this is all the same. It's just to look good in benchmarks, which is insane. Because if you do the wrong thing fast, it's like the opposite of what I want. If you're going to do the wrong thing, then please do it as slowly as possible so we can stop the accident. Okay. So file systems are complicated. The APIs are a mess. Let's take a step back to make things a little bit simpler. So we started a partnership with IBM. They are making these things. It's a CAPI flash card, and it has an FPGA. That's basically a programmable chip, and you can upload microcode to it, and it'll reprogram itself to be any other kind of chip. And these two are M.2 SSDs disks. SSD, yeah, not disk. And they expose a user space block device API that we are integrating with, and we are making Neo4j work on top of this as a kind of storage system. So it exposes a block API, and like I mentioned, we are working with files, so we kind of need a file system in between. But we don't need very much file system. If we have direct, positioned, vectored read and write, that's all the I/O we need. We need to create, truncate, and delete files. We don't need any pre-cleaning or zeroing of allocations. Real file systems, they do need that, because if you create a file, then write like 1,000 blocks over the end, then you want the space in between to be 0. You don't want it to be old deleted files suddenly reappearing inside your files. We don't care about that. So we need to rename, because we occasionally, for instance in HA, we copy stores over when we add more members to the cluster, and then we put it in a temporary store, we rename it, stuff like that. We need big files. As it turns out, ext4 only supports up to 16 terabytes. Our store format supports more, so yeah, why not? And then we only have a small number of files. In the store, we actually only have like a dozen, so we don't have very big requirements in that regard. So this is what I've been working on for a little while. It's a database file system, or dumb block file system, because it doesn't do very much. It only has the features I mentioned. And then the file size, it uses 64 bits for addressing blocks. So, and you can have a file as big as your device. So basically exabyte sizes. And and it supports transparent heterogeneous device striping, which is like, I'm going to talk more about that. It's a cool feature. And then because we only have a small number of files that we actually need, then it supports up to 500 files and no directories. Who needs those? So device striping, it's basically taking, a question?
Was it 500 and not the 512?
Actually, it's 511 because there's like a magic number at the end, so I can tell whether the device has been formatted or not.
Oh.
So that was a typo. 500 is a typo. Approximation.
500, you're not going to use all that. So device striping is, if we look at the card, we can see it has 2 SSDs. And there's one card, and you can have more than one card in a machine. So, which is the diagram here. So we take these devices, and in the old version, the picture is version 2 of Cabby Flash. In the old version, you have fiber channel attached big boxes of flash. So the 2 devices can actually share a same namespace. So we support that as well. You can take these devices and then you present it as a single virtual giant disk or drive by striping over 16 megabytes at a time, and then just round robin distributing the access. So if we assume a uniformly random access on the virtual device, then we'll get a uniformly random access to the hardware below, which is desirable for getting more throughput, more parallelism out of it. And that's basically what I'm trying to say with this picture. The ponies are the SSDs, and then they're driving the database forward. Yeah, and we can see the parallelism opportunity directly with the 2 SSDs on the card. And you can have...
Those are just standard M2 disks?
Yes, using NVMe. So latency is quite low, but it's still standard NVMe SSD latency.
Right.
Then you add a tiny bit for the FPGA on top of that latency. But the point is that you get the throughput and the parallelism.
Right.
So the FPGA acts as a controller, and it's quite powerful.
How does the kernel talk to that device? What's the driver for that? Is that a pretty standard thing as well, or is that very custom?
It's pretty custom. So this FPGA, it attaches to the power service layer and then talks to a Power 8 chip that has this protocol built in.
Right.
So so I think they are doing this with kernel bypass, and then they have dedicated threads to handle interrupts. So it's not polling, it's interrupt based, but it's still pretty fast.
Cool.
Yeah. So this striping all happens in the block layer. On top of this single virtual device, we put our file system, so that becomes simpler. And the basics of it is we have a master block that's on LBA 0 always, and here's your 500 and up to 11 files. They're just like 8-byte pointers to logical block addresses, and then with the bit of magic in the end, and then a version, so you can modify the format later should it be necessary to add features. And then we also keep some stuff in memory. We have just a list of all the root inodes. A root inode, so an inode means index node, so you can index into files, and the root of that's a file, so they contain the file name. And then we have a navigable set of all the inodes, so there can be more than just the roots. So when we add a new file, initially when we format the device, we just have the master block with this little magic number. And the first file that we add is on LBA 1. So we just put it there, and then we assume that all the space following it until the end of the device, it's for this file, because why not? And then on the second file you add, we find, or any other file after that, we go look for the largest contiguous bit of free space. And we cut it in half and add the inode in the middle, so the first half of the free space goes to the old file. It gets to keep that, and then the second half gets allocated to the new file. So that's what happens here. We take this free space, cut it in half, and then the new file starts from here. The old file keeps going here. So if the old file fills up this space, which can happen, then we do the same thing again. We go look for the biggest contiguous bit of free space, cut it in half, then we add a continuation inode in the middle, and then the file goes from here, continues down here.
How big is the master block?
There's one block, 4K. And then each LBA is 8 bytes. Do the math, 511 files. So we end up with a structure of inodes that look like this. We have the master block, which is like the root of a tree, and then each root inode is just a linked list of continuing regions of files. And they're ever smaller regions as we keep dividing the space. But we're not going to do this very much because we know that there's only about a dozen files that we actually need. So we're not going to have very much metadata.
And you don't have to ever worry about fragmentation because it's solid state, right? So it doesn't matter where you're accessing. Or does that make sense?
So far, I have not mentioned files shrinking ever, which makes fragmentation a non-issue.
Okay.
Because data never goes away. Yet. So the inode, it has this pointers to the continuation if there is any, and then also if it is a continuation, it has a pointer back. The reason it has a pointer back is only so we can consistency check the metadata. Otherwise, just singly linked list would be enough. And then the limit is the LBA of one beyond the last usable block in the current allocation, in the current region. So so that would point to the next inode in LBA order, or one LBA beyond the device boundary. And the size is just the number of blocks that we actually use in this region. The capacity is a bit similar, but it extends beyond the size if we are appending to the file. So that works by first increasing the capacity. This means that this space is now reserved. So if another thread comes along and it wants to find some free space to split in half, then it won't take away the space that we are appending into. And once we've done the write, then we can increase the size of the capacity and the file has grown. The rest, if this is a root inode, then the rest of the space, because we have a 4K block, the rest is just the file name. And it can be anything except null.
So the bigger the file, the smaller the file name can be.
No, this is just one inode. These are all 8 bytes.
Oh, right.
So the rest is just some weird number for the file name. So we support longer file names than X4, except they have directories, so they're cheating. Okay, so truncation and deletion are a little bit more complicated because they work in the opposite direction than adding data to the system. Deletion is basically just truncation, where we also remove the root inode. And we support truncation to any part. Truncating to 0 is the most common case. And the way it works is that we take a lock all the way down the chain, because we're always gonna, when we truncate, we always remove from the end. So we go all the way to the chain, and then we either update the size and capacity if the truncation target falls within this region, or we remove the inode entirely. And then we go back and we unlock as we go back. So we keep the flow of the locks. And this locking order, starting from the top going down, makes sure that we never have any deadlocks within the file system, which is a desirable property. So when we delete inodes, we can end up in a situation where a region that previously did not have any space, so it added a continuation to continue the file in another place. Suddenly it can get free space, but we cannot actually use it in that region because the order of the regions in the linked list and the orders of the blocks within the region determines where in the file this block lives. So if we were to add blocks in this region here, we would actually change the location of all the data following it. So when I added support for deletion and truncation, I had to update the allocation algorithm or the allocation strategy, because just bisecting free space is no longer a clever idea. So we look for these patterns where we have a region with a continuation and free space. And then we don't cut it in half, we just take all of it. So we end up with a similar pattern to this. And this way we avoid fragmenting. So that's the gist of it. All reads and writes are direct and synchronous, and unlike the normal file system, there's a one-to-one correspondence between our pages in memory and blocks on the file system. That's not the case on a normal file system, where the pages we map into memory may not match exactly onto blocks or sectors on the file system. And this means that if we modify a page and it doesn't entirely overwrite a block, it only overwrites part of it, we actually have to read that into the operating system page cache, overwrite most of that data.
Press the key
So we overwrite most of the data that we just read in, and then write it back. And because it's a read, we have to wait for it. Writes can be buffered, they can be put in queues, you can just send them off and forget about them, but reads you have to wait for them to actually complete before you can do anything with the data. So that's can be a big source of slowdown. We don't have this problem at all in this setup. So we also have no journal, and we instead rely on careful ordering of updates to the metadata, like I explained. When we append to the file, first we update the capacity, then we do the write, then we update the size, stuff like that. So we don't need a journal. We could add a journal to amortize the cost of 2 metadata updates whenever we append. We don't have to, because it doesn't appear to be a problem in practice. And then we have very low metadata overhead with the bisecting and with the size of these regions and the few files we have. Most file systems today are actually based on extents, so they have these contiguous big regions that they try to allocate, because it's quite nice to have sequential big regions of files. And they try to be quite clever and sometimes merge extents or move them around. But they don't support the same size that we do. XFS supports up to 8 gigabytes, but X4 only supports 128 megabytes. So this means that even though they save a lot of metadata by using these larger regions, they don't save as much as we do. And because the regions are so large, we get very good sequential access sympathy. And for the same reason, we have so little metadata that we can keep all of it in RAM all the time. So we never need to do any I/O for traversing the file system metadata. This means that we also get good random access sympathy. And last bit, the Neo4j is open source, both the community version and the enterprise version. Even though we try to sell the enterprise version, that's the business model. It is actually open source, and because this requires special hardware, we are experimenting with making this component closed source. So this is the first time that we are trying to do this, because the C libraries for the block device APIs that IBM is working on for the Cappy Flash, those will actually be open source. But I don't know about the firmware that goes into the FPGA, and obviously you have to buy the hardware in the first place. That's their business. So these are
Loader is also closed too.
probably, yeah. It might even be possible for IBM to open source that, because that's a different company making the FPGA itself. So yeah, it's a closed source add-on to the Enterprise Edition. It's maybe in technical preview, I don't know. It's around that time. So
Who are buying Cappy Flash can afford to pay for Neo4j Enterprise.
I would imagine so.
I'm
Just-
pretty sure the Neo4j license is
Yeah.
a portion of the Cappy Flash.
Yeah. I heard some really nice prices for some of the big systems where they include this. So. Yeah. Any questions? Yes.
Is this implement like a kernel module or something like that, or is it a standalone thing only in user space?
It's entirely in user space.
So it's not possible to
Yeah.
Use the same file system on a like SSD or something. It's not made for that.
So the file system works with a very thin block device API abstraction that we've written, and that's the Cappy Flash specific part. So we could write another implementation that works with Linux raw devices or SPDK, and then we'd have the same feature working there. So for this reason, we are kind of considering, but we haven't decided yet, if the file system itself should be made open source, and then we just keep the block device parts closed, or if it doesn't matter, and we just keep it all closed source. We haven't figured that out. Yep.
Do you have you had access to hardware for testing this, or how do you test it without the hardware on your desk?
See, we have there are three options. So IBM, they gave us this C header file, and I just implemented that by saying, you allocate a big file and memory map it, and that's your device. And then I just re-implement the same APIs. Another option is that they actually build a test implementation of this API. So you can also get like a more real test version of the library. And then of course the third option is to actually have the hardware. And we've tried both the hardware and my hack code, and they both seem to work. But we don't have a build running continuously with the hardware, because it's a little hard to get access to. So, but that's part of what we're working on. That needs to happen before it can be like GA, which is we're scheduling to go GA with this support in 3.1, and then there's tech preview beta support for certain partners in 3.0 something. Yeah.
What is this conceptually similar to in terms of other file systems? You're talking about X4 and XFS.
I guess
Is it
it's
like Minix FS, or is it closer to UFS or?
Perhaps it's closer to whatever CPM did back in, I don't know, 60s or 70s, because it's so simple. Like
It's Fat 12.
no, it was a file system that had 16 regions, and they were like top level directories, and then you could put your files in there, and that was it. You can't go deeper.
Right.
So you had 16 lists of files. Well, that's even more advanced than what I have here. But I do have support for just / in file names. That's fine. So you can sort of have, then you can list the files and use regular expressions to search for what you want. And it's going to be quick because you only have at most 500 or 511.
So what's the performance like compared to other file systems with specific, quite specific use cases? Like benchmark?
Yeah, we have a fairly complicated benchmark that we've been running with IBM on top of this, and it's been seeing 2.5 times improvement. Part of it is the avoiding the read modify write cycle. Something that's holding it back is that it's when you're running a database, which is what the benchmark does. You're not just running the file system; you're running an entire query engine with the transaction state on top of it. So the file system ends up being a small part of it. And then, of course, the CAPI flash is just the card with the FPGA. We still have normal SSDs, M.2 and NVMe. They're fast, but they are not like beyond what you can go out and buy. So the advantage is mostly in the parallelism that we get and the throughput. But the latency is good, but it stays about in the general area of normal SSDs. Yeah. Any other questions?
You were talking about number of lines of code and quality.
Yeah.
Simplicity here. So
Yeah.
how, what does the metric say?
How many lines of code? I think it's 2,000. It's Java, includes like your Java docs.
Minix FS is 4,800. Just under 5,000. That's an improvement.
They have the disadvantage of working with C. I don't know. We also put curly brackets on separate lines because that's the new OpenJ code standard, which is funny. So it's small. All right. Thank you.